Okay, so this is dynamics part 2. We have covered about Newton's three laws of motion in the previous chapter or previous session. Today we will be covering about free body diagram and vector diagrams in this section. Okay, so these are the learning outcomes. Okay, but before we start, let's do a very quick recap of what we have covered in the previous session. Okay, you may pause the video to think about the answers to this question. I'm going to go through the answers now. A car of mass 1000 kg is moving with an acceleration of 2. Find the force that the engine exerts on the car if the car is moving on a road with a constant friction of 1000 Newton. So in this question, it's very obvious that I'm not trying to find the resultant force. I'm trying to find the engine force. Okay, so immediately in my head, I need to know I am going to use for resultant force equals to forward force, which is the engine force, minus the backwards force, which is the frictional force. Okay, and since this car has an acceleration of 2, definitely it must have a resultant force. So the first step I will do is I will find the resultant force. Okay, so I have mass, I have acceleration, I could find the resultant force. So the resultant force acting on this car is 2000. And then I'm going to use the formula forward force minus backwards force equals to resultant force. So my engine force is my forward force that pushes the car forwards, minus the backwards force, which is friction, will be equals to resultant force, which is 2000 newtons. And when I sub in, engine force will be 2000 plus 1000, which is the frictional force. So in the end, I will get 3000 newton. That will be my engine force. For the second question, which of the following is true for every object experiencing zero acceleration? So you should know that when I have zero acceleration, I will have zero resultant force. But zero resultant force does not necessarily mean that there are no forces. It's just that all the forces are balanced. So the best answer over here is it has zero resultant force, not no forces. Okay, let's move on. So in this part, we'll be covering free body and vector diagrams. What are actually free body diagrams? Free body diagrams is just using arrows to represent the forces that acts on individual objects. Okay, so the purpose of drawing free body diagram is to help us identify and visualize the force that acts on the object. And it also helps us to solve problems about forces. So we can see clearly on each individual object what are the forces present and in which direction are these forces acting on the object. Okay, so before we start, we need to identify all the different types of forces that are possible. Okay, so I'm going to introduce to you some of the common type of forces available. And then we will try to apply them into questions later on. Okay, so the first one, very common, okay, for all objects on Earth, that or mostly all objects, there will be a force called the weight or the gravitational force. And then the gravitational force is always drawn from the center of the object, or we call it the center of gravity of the object, which we'll cover in the next few chapters. Okay, it is always from the center of the object, and it is always acting vertically downwards. Okay, so it looks something like that. If I have a box, then the center of gravity, or the weight will be from the center of the box downwards, vertically downwards. And if I have a spear rolling down a hill, okay, the weight is not along the hill sloping down, the weight is still vertically downwards from the center of the object. Okay, next we have something called a normal force, or we call it a contact force. Okay, this happens whenever an object is touching a surface, is in contact with a surface. And you must know that for this normal contact force, it will always be 90 degrees upwards. It will always be perpendicular upwards from the point of contact. So I give you a few examples. So if I have a box like this, touching the ground, then the normal contact force will be diagonally upwards, vertically upwards. And then if I have it on a slope, then the normal contact force will again be 90 degrees or perpendicular to the surface upwards. Okay, and then next we have air resistance. Air resistance occurs whenever an object is moving through air. It might not be dropping down, it might be moving forward or backwards. As long as the object is moving through air, okay, it's some kind of like friction in the air. It always opposes the motion of the object. So for example, I have two examples here. I have a parachutist dropping down. Okay, the resultant force is downwards. Okay, it's moving down. Okay, then as it moves down, that there is air resistance, okay, against this parachutist. So the air resistance is against the motion, which is downwards, so the air resistance will be upwards. Okay, similarly, if I have a block moving to my left, if I have a block moving to my right, okay, so this block is moving to the right, then it will have air resistance acting on it as well. The air resistance will be opposite to the motion, which will be to the left. Okay, next. Okay, we also have something called friction. Friction occurs whenever an object is in contact with a surface and the object must be moving. Okay, same like air resistance, it always opposes the motion, and friction must be drawn on the surface of the object. You cannot draw a friction in the mid-air. Friction must happens on the surface. So for example, if my box is moving to the right, then the friction is to the left, and the friction is between the box and the floor. It must be along the surface. Okay, so another example, I have a box sliding down the slope. Okay, so the movement of the box is sliding down, the friction will be opposing it, so the friction will be upwards along the surface. Okay, next we have tension. Tension is present whenever there is a string, and we always take it as tension is always pointing away from the object. Okay, so for example, I have a string holding this box, a string holding this box, or a string pulling this box. Okay, so the tension is always, we take it as is always away from the object. Okay, next we have a thrust or engine force. This is a pushing force to cause some objects to move. Okay, and then just take note that all the forces must be drawn on the body, and it must be drawn using a ruler. Okay, so for free body diagram, the arrows must start from the body. Okay, so the position of the force as well as the length of the force matter. Okay, so if we have a larger force, we will draw the arrow, we will draw it with a longer arrow. So the longer the length, the larger the force. Okay, so this can be found in your textbook. These are certain examples of forces of free body diagrams on objects. Okay, so you can see over here, let's start from the bird. So the bird, there is a thrust force by the wind, by the wings. Okay, and then as the bird flies, it moves through air, so there's an air resistance backwards. And then there is a lift force by the wing, and there's a weight caused by the earth, gravitational field strength. Okay, so these are the four forces acting on the bird. Next one, an apple that is hanging on the tree. Okay, so there is a tensional force in the stem of the apple. Okay, and then or the stalk of the apple, and then there is a weight pulling it down, and then as it drops through the air, okay, when the apple drops down, there is a weight pulling it down, and there is air resistance. The arrow should be on the apple, not in the middle of the air. Okay, and then this one, when it touched the ground, when the apple drops and touch the ground, there is still a weight, and there is a contact force upwards on the apple. Okay, so these are some examples. Next one. Okay, so I have a box suspended by two strings over here. Okay, so the two strings will give me a tension force in the string, and there is also a weight acting on the box. Okay, and then next one, we have a rocket in flight. So the rocket is flying up. Okay, so there is the force of engine or the engine force upwards that cause the rocket to fly up. And as the rocket flies up, there is an air resistance acting on the rockets, which is represented by this pink arrow. And also, beside air resistance, the rocket also has a weight that is going downwards. Okay, so these are all the forces acting on different objects. Okay, and one very common one that they like to use in O-level will be look something like this. You have a box on a slope. Okay, so what you have to draw the free body diagram of this box. So naturally, I have a box. Naturally, from the center of the box, I will have a weight vertically downwards. And then since the box is touching the slope, I have a contact force upwards that looks like this. And then as the box slides down the slope, I will have a frictional force backwards, which is going upwards like this along the surface. So these are the three forces acting on a box that is on a slide. Okay, you can try to scan the QR code to work on more examples of free body diagrams. Okay, let's move on to some examples. Okay, so you have a car of mass 700 kg can exert an engine force of 5,000 Newton when it travels along a road, and it experiences a friction of 100. So the engine force is actually the forward force that pushes the car, and the friction is the backwards force. So draw a free body diagram to show all the forces acting on the car. So I usually just draw a box to represent the car, the object. Okay, so I have a weight, which is 700 kg or 7,000 newtons. I have the engine force, which is moving forward at 5,000 Newton. And then I have a frictional force between the road and the car, which is on the surface of the material, is frictional force of 100. And since this car is touching the floor, there is a normal contact force. Okay, so this is how it looks like for a free body diagram for the car. Next, using the free body diagram, calculate the resultant force and therefore the acceleration. So we come back over to here. The weight and the normal reaction force are balanced because the car doesn't move up or doesn't move up into the air, doesn't float in the air, or neither does it move down into the ground. Okay, so the only two unbalanced forces is the friction and the engine force. And in order to find the resultant force, I am going to again apply the formula forward force minus backwards force. So the forward force is the engine force minus the backwards force, which is the friction force. So I have a resultant of 5,000 minus 100, 4,900 Newton. And because of this resultant force, I will have acceleration. So in order to calculate the acceleration, I will use F equals to ma, whereby my F is my resultant force, 4,900. Then divided by the mass, 700 kg, I'll get my acceleration of 7 meters per second square. Okay, next, okay, we move on into vector diagrams. Okay, vector diagrams are different from free body diagrams. Vector diagrams is using a scale and graphical methods to find the resultant force whenever you have forces that act at an angle to each other. Okay, in the previous few examples, it's very easy to determine the resultant force because the individual forces are all parallel to each other. I either act in opposite direction or in the same direction. So I either plus or minus. But forces do not necessarily act parallel to each other. They may act at an angle with each other. So in order to solve this, we use vector diagrams. So there are two ways to construct a vector diagram. There's the first one, which is a parallelogram method, and a tip-to-tail method. Okay, we will go through both of them. But for pure science, it's preferred to use the tip-to-tail method. Okay, so this is how it will look like for parallelogram method and tip-to-tail method. So I have two forces. One of them is 5 Newton and one of them is 3 Newtons. And these two forces are not parallel to each other. So 5 Newton is 40 degrees to the horizontal, and then 3 Newton is 20 degrees to the horizontal. So they are acting like this. Okay, I know that as a result of this 5 Newton and 3 Newton, I will have a resultant force towards the right side somewhere here between the 5 Newton and 3 Newton. But how do I determine this resultant force? Then I use what we call a vector diagram with a specific scale. So for example, over here, I will have a scale. 1 cm represents 1 Newton. So I'm going to redraw these two purple lines, which are my forces, according to the scale and according to the angles labeled. So I'm going to draw 40 degrees and a 5 cm line, and then I put an arrow to indicate it's a force. So it's 5 newtons, and then I measure again 20 degrees. I draw a line 3 cm, and then I label it with an arrow to show that it's a force, and I label it 3 newtons. Okay, then what do I do for parallelogram method? I complete my parallelogram. So I'm going to shift this entire 3 Newton line upwards. Okay, so I'm going to use it, shift it upwards. This is not a force, this is just construction lines. So I'm going to use it as a dotted line. So this line will be exactly the same as this 3 newtons at the bottom. Okay, so so after that, it will be also 3 cm. And then same for this 5 newtons, I'm going to shift it downwards over here. So it will be 5 cm. And then my resultant force will be in between this 5 and 3 newtons, which will be this orange line. And the resultant force is represented by a double arrow over here. And I were to measure the length, it will be 7 cm, which also means it's 7 newtons. and it makes an angle of 18 degrees with respect to the horizontal. Okay, tip to tail method is slightly different. Tip to tail method, I just keep one of the forces. In this case, I keep my 5 Newton. You can choose to keep the 3 Newton first, it's fine. So in my example, I keep the 5 Newton. Okay, so after the tail of the first one, I go to the tip of the second one. So I'm going to shift this 3 Newton force upwards. Okay, so that it continues after the 5 Newton. So I have 5 Newton up like this at an angle of 40. And then I'm going to shift my 3 Newton down like this. Okay, and 3 Newton is at 20 degrees to the horizontal. So I need to label my angles well. Okay, so I will have like this 5 Newton, then followed by 3 Newton. So my resultant force is starting from here at the start of the 5 Newton all the way until I end up after 3 Newton. So this will be my resultant force, which is represented by a double arrow. It's the same for both cases. Okay, you will measure that the resultant force will be also 7 cm, which will be 7 newtons, and it will also be at an angle of 18 degrees to the horizontal. Both will give you the same answers. Okay, let's look at more examples and look at step by step the procedures. Okay, you have a frame picture hang from a nail on the wall. The picture is held up by 2 strings which can support 25 newtons each. What is the weight of the frame picture? So step number 1, every time when you want to find one of the forces, or 2 of the forces, you need to ask, and you need to draw vector diagrams because the forces are not parallel to each other. You need to think whether there will be a resultant force or not. So in this case, my frame picture hanging on the wall, my frame picture is not moving at all. So I would say that there will be no resultant force acting on this frame picture. Okay, I have a tension in these 2 strings. So the tension of these 2 strings will be over here. And each tension will be 25 newtons. 25 newtons. And because of these 2 strings pulling up, I will have a resultant force upwards. Okay, this resultant force upwards will be balanced by the weight of this photo frame. Okay, it will be balanced. The upwards force and the downwards force caused by the weight will be balanced. And that's why the picture frame will not move at all. The picture frame will be stationary. Okay, so let's take a look at how do we solve it by parallelogram method. Okay, so step number 1, for parallelogram and for tip to tail, step number 1, we always need to choose an appropriate scale. Okay, our scale should make it such that it will occupy the space that is given. Okay, but it should not exceed over the entire piece of paper. Okay, so the first one, your scale should be 1 cm represents a certain amount. Okay, this will be correct. Okay, but we cannot put our scale as 2 cm represents 10 newton or 5 cm represents 20 newton. It must always be 1 cm representing something, not 2, not 3, not 4, not 5, or not 10 cm represents something. Always 1 cm represents something. So in this case, my previous example, I only have 2 forces given, 25 newtons, 25 newtons. So I thought 5 newtons, 1 cm representing 5 newtons would be a good one. Please do not give me very weird numbers like 1 cm represents 5.9 newtons. It's very weird when I do my calculation. So 1 cm represents 5 newtons is good because I just need to draw 5 cm and 5 cm. Okay, so that will be my scale. Step 1, okay, this will give you 1 mark. Step 2, you need to redraw the forces in the same orientation. What do I mean by same orientation? Okay, it means that my 2 forces are like this, 25 newtons and 25 newtons. I need to redraw them according to the scale. That means I need to redraw like this, exactly in this direction at 40 degrees to the horizontal. 40 degrees to the horizontal. Redraw this whole thing. Okay, redraw it according to the scale. So I need to redraw. I need to measure 40 degrees and measure 5 cm, 40 degrees and measure 5 cm upwards. Okay, so this is what I mean by that. And then label it with the arrows and label it with the magnitude, 25 newtons. Okay, then next I know that my resultant force will be upwards. Okay, so how do I do it? I complete my parallelogram, okay, using dotted lines because parallelograms are not real forces. So I complete it using dotted lines. Later on, I'll show you the final product. Okay, so after I complete my parallelogram, I need to determine the resultant force. So the resultant force will be upwards like this. Okay, and then the resultant force is a force, so it will not be a dotted line. It will be a bold line with double arrow. Double arrow is to indicate that it will be the resultant force of these two tension. So after that, I measure the length of the resultant force. Okay, and I multiply it by my scale. So if my length is 5 cm, I'll be 5 times 5. If my length is 7 cm, I'll be 7 times 5, 35 newtons. Okay, and then I measure the angle of the resultant force with respect to one of the known forces. Okay, so I can measure the angle that this resultant force makes with the 25 Newton force. Okay, so this will be the direction of my resultant force. So I give you an example how it looks like. It will look like this. First step, the scale. Second step, okay, I'm going to redraw the two forces according to the scale. So I'm going to measure 40 degrees, and then I'm going to measure 5 cm, 5 cm. To get my 25, I draw my arrows and label it with forces. So I know that these two lines are actually representing force. Okay, next, then I complete my parallelogram. Okay, so this green dotted lines are my parallelograms. It should also be 5 cm, 5 cm. Okay, and then I determine my resultant force. My resultant force will be upwards from one end of the parallelogram to the other end of the parallelogram. So this will be my resultant force, and I measure the length. Okay, multiply by 5 newtons. I get my length is the resultant force is actually 32 newtons. Okay, so if I have a resultant of 32 newtons caused by these two tensions, then the weight of my picture frame will also be 32 newtons. Okay, in order for this picture to remain stationary. If there is no weight, then this 25 Newton and 25 Newton caused by the tension will cause this picture frame to move up, but this picture frame is not moving up. So there must be a downwards force of equal magnitude, 32 Newtons to balance it. So the weight of this picture frame will be 32 Newtons. Okay, next one, we go into tip to tail method, okay, which is the preferred method. Again, the same first step is to choose an appropriate scale. Okay, so again, we are going to use 1 cm represents 5 newtons. Remember, 2 cm represents something, 5 cm representing something is not acceptable. Only 1 cm represents something. Okay, next one, we make a rough sketch of how the diagram will be like, okay, at the site, and we label all the important angles on your sketch. Okay, it's important to do that so that you know where should you start drawing your diagram. Should you draw your diagram from the top or should you draw a diagram from the bottom? And when you do a sketch, it's easier for you to visualize what are the angles between the forces so that you know how to continue when you're drawing your actual diagram. So you just make a rough sketch. You don't need to measure the length, don't need to measure the angles, you just label them. Then after that, you redraw one of the forces, any one of the forces. Redraw one of them in the same orientation and according to the scale. So I have 25 newtons given. I need to just keep one of them and redraw it according to the scale. So which means I need to draw exactly 5 cm and exactly at 40 degrees to the horizontal. Then I label the force with arrows and magnitudes. And then after that, I need to shift. I only keep one of the force. The other force, I need to shift it such that the tip of the force, of the previous force, okay, or the tip of this new force is at the tail of the previous force. And the angles must be accurately calculated. Otherwise, your final reading will be wrong. Then I determine the direction of the resultant force, draw in the resultant force with double arrows, and I measure the length and measure the angle. This will be the same step as for your parallelogram method. So let's come and take a look at this. Okay, so the picture frame is stationary, means resultant force is 0. So actually, the first thing, I hope you can recognize that there are 3 forces acting on this object. There is the tension in this 2 string, and there is the weight of this object. Okay, so these 3 forces acting on the picture frame is causing the picture frame to remain stationary, not moving. Okay, so first step, I have a scale. 1 cm represents 5 Newton. Then after that, I'm going to keep one of my forces. So I am going to keep this first force up, sliding up like this. Okay, so I redraw it according to the scale. So I measure exactly 40 degrees to the horizontal, and then this line is 5 cm, and I label it with arrow and label it with the force, 25 Newtons. Okay, for my second force, I'm not going to redraw it. I'm going to shift this second force, sliding up one. I'm going to shift it until it is at the until the start of this force is at the tail of the first force. So if I were to shift it, I'm going to shift it upwards like this. Okay, so again, I draw the horizontal normal 40 degrees, and I'm going to shift it up. So this second force over here is shifted up like this at the same angle of 40 degrees to the horizontal. Again, this force will be 5 cm, and then you draw with an arrow in the center and label it the force to know that this is a force. And after these 2 forces, I still have one more force downwards, which is the weight. So the weight, okay, will continue after the second force. So the weight will be vertically downwards, and the length of this weight that you get is exactly 32 Newtons. Okay, I will measure this length, and I will get the length times 5 Newtons, I get 32 Newtons. So this red color line actually represents the weight. So in a tip to tail method, you can see that there is no resultant force. I start from this point over here, okay, and then I have my force going up 25 Newtons, going up again 25 Newtons, and I have my weight going down 32 Newtons. I go back to my starting point. So there is no resultant force acting on this frame at all. Okay, so this is how I use the tip to tail method. Okay, so some useful notes on vector diagrams. For vector diagrams, if the arrows all end up in a closed triangle like this. So for example, I start my force from here, this dot over here. I go up diagonal, I go horizontal to the left, and then I come down. Okay, I start here, I end here, there is no resultant force. That's what we call a closed loop triangle. We say that all the forces are balanced or are in equilibrium. Equilibrium is balance. Okay, but in certain case, there will be a resultant force. So over here, you will see that there are 2 forces, and because of these 2 forces, it results in a resultant force. So my starting point is over here. Okay, I have a force that goes diagonal up, and then after that, I continue with the force going diagonal down. I will end it here. So this is my start point at the bottom, and this is my end point at the top. So my resultant force will be a straight line with double arrow to represent the resultant of these 2 red lines, or these 2 red force. My resultant force will be like this, sloping up. Okay. Okay, then you may scan this QR code to give you various examples of how resultant force can be determined using the parallelogram method. You can choose the following things to take. Okay, just by taking this first 2, you should be able to see how a parallelogram works. And you can also try tip to tail method, where you just take this 2 box. Okay, it's called the triangle method as well. Okay, that's it for this part.